Hello. What I'm going to do in this video is solve a calculus final from a recent semester. There are several multiple choice questions and followed by some free response questions. Okay, so let's take a look at this. Number one, it says, let f be a function defined on negative infinity to infinity, so it's defined for all real numbers, such that f of x is between sine x and 2 times the absolute value of x for all values of x. Which of the following can be determined? Okay, so, well, let's take a look. Can you determine the limit as x approaches 0? Well, let's see. You have that sine x is less than or equal to f of x is less than or equal to 2 times the absolute value of x for all values of x on the real line. So, by the squeeze theorem, you must have that the limit as x approaches 0 of sine x and the limit as x approaches 0 of 2 times the absolute value of x will squeeze in between them this limit as x approaches 0 of f of x. What do you know about this? This limit is 0, right? What about this? You know that this limit is 0. So by the squeeze theorem, the limit as x approaches 0 of f of x exists and it equals 0. Okay, so you have that that is correct. Now, what about f of 0? Well, you know that this statement is true for all x's. So you have that sine 0 less than f of 0 less than 2 times the absolute value of 0. The right-hand side is 0, the left-hand side is 0, so you must have that f of 0 is 0. So you know that is true as well. Now let's look at the third thing, which says that the limit as x approaches 0 of f of x over x. Okay, well, let's see. So you have limit as x approaches 0 of f of x over x. Well, first thing, I just want to point something out over here. You know that since f of 0 is 0, this really is limit as x approaches 0 of f of x minus f of 0 over x minus 0. Just something to notice, that if this limit existed, then it would be f prime of 0. Okay, it would mean that f is differentiable at 0 and this limit equals f prime of 0. Okay? Okay, all right, so just something to notice that that's what this is since f of 0 is 0, which we know from having looked at this over here. Okay, well, let's take a look at this. How will we even get our hands on this? The way we get our hands on this is using this inequality that we are given. Okay, so let's look at this inequality. Okay. So we have sine x less than or equal to f of x less than or equal to 2 times the absolute value of x. All right. So first what I'll do is try and look for the limit as x approaches 0 from the right. So we divide by, so x is positive, so divide throughout by x, and you have this. Okay, and limit as x approaches 0 from the right or left. In either case, this one is 1. Okay, and limit as x approaches 0 from the right of this, what will it be? The absolute value of x is just x. This limit is 2. So you have limit as x approaches 0 from the right of f of x over x is between 2 and 1. That's all you can say. You don't even know if that limit exists. If it exists, this is what you would have. You can't, using this, decipher that it does exist. So we can't even talk about that. Okay? So we have that. Now suppose we were looking at limit as x approaches 0 from the left. Sine x over x, we know that is 1. How about limit as x approaches 0 from the left of 2 absolute value of x over x? What is this? The absolute value of x is negative x, and this would be minus 2. So you know that this limit as x approaches 0 of 2 absolute value of x over x is either negative 2 or 2, depending on whether you're from the left or the right. This is always 1, so in that case we can't say anything about this. Now if those two limits were equal, then we could say by the squeeze theorem this limit equals whatever it is. But in this situation, we can't say anything about this limit, so all that we can say is this limit exists as x goes to 0 of f of x, and we know that f of 0 is 0. Okay? So we can't say that this limit exists, nor can we say that f is differentiable. Okay. All right, so let's look at this next problem. F is a function that's continuous. So limit is such that limit as x approaches 5, f of x minus 7 over x minus 5 is 3. Which of the following claims must be true? Okay, well, let's take a look. Well, in the first place, we know that f is continuous. Of course, if f is continuous, limit as x approaches 5 f of x must exist. It's got nothing to do with this. Okay? And let's look further. What do we have next? We know that this limit exists, okay? So let's write this down. The limit as x approaches 5 of f of x minus 7 over x minus 5. This limit exists, and it equals 3. Now, what does that mean? My claim is that that would mean that the numerator, this limit must be 0 too, okay? Why? Well, here's why. If limit x approaches 5, f of x minus 7 is not equal to 0, okay? That is, but what is this? This is limit as x approaches 5 of f of x, which exists because f is continuous, minus 7 is not equal to 0. But what is this? Since f is continuous, this is f of 5 minus 7 is not equal to 0. So if you have that this limit as x approaches 5 of f of x minus 7 is not 0, or like I said over here, in other words, if f of 5 minus 7 is not 0, then what would happen? You would have a non-zero number in the numerator over 0. And if you have that, then this limit would be plus or minus infinity, okay? Okay, so you must have that the numerator also goes to 0, and the numerator going to 0 means that f of 5 minus 7 goes to 0. So you must have that limit x approaches 5 of f of x minus 7 equals 0, which is limit as x approaches 5 of f of x minus 7 equals 0, or limit x approaches 5 of f of x is 7, but by continuity of f, this must be f of 5. So you must have that f of 5 is 7. So since you have that f of 5 is 7, what is this? This is f of 5. So what does this become? This is limit as x approaches 5 of f of x minus f of 5 over x minus 5. Well, that means that this limit exists and it equals 3. Well, if this limit exists and it equals 3, it must mean that f is differentiable at 5. And, of course, that the derivative is 3. And by this argument that I just discussed over here, this tells you that f of 5 must be 7. Because if f of 5 isn't 7, like I said, this numerator is non-zero, this is 0, so you cannot get a limit of 3. Okay? So in this case, you have that all these 4 choices are true. All right? Okay. Let's look at this next problem. You need to find the limit as x approaches infinity of square root x raised to 1 over x. Well, what is this going to be? As x approaches infinity, it would be of the form infinity raised to 1 over infinity, so infinity raised to 0. Okay, so what do we need to do? We need to apply L'Hopital. All right, so square root x raised to 1 over x will be e raised to ln square root x raised to 1 over x. Okay, which is e raised to 1 over x ln square root x. But you know ln a to the r is r ln a, so we could just simplify it a tiny bit further and write it like this. Square root x is x raised to 1/2, and this will be e raised to 1 over 1/2 times 1 over x, so 1 over 2x ln x. So we have to find the limit as x approaches infinity of square root x raised to 1 over x, which is going to be the limit as x approaches infinity of this, but exponential is a continuous function, so it'll be e raised to the limit as x approaches infinity of 1 over 2x times ln x. Okay, so what we need to do is find this limit. Okay, all right, so let's find that limit. Okay. And I'm going to rewrite it as ln x over 2x because it's much easier to deal with like this. Now let's take a look at this form. What form is it? Of course, since we got it from a form involving L'Hopital, that's what we'll get again. This is log of a number getting bigger and bigger, gets bigger and bigger, so that's infinity over infinity. Okay, so we can apply L'Hopital. Make sure you always explain why you are using L'Hopital, that show that it's an indeterminate form. So by L'Hopital, what do you have? You have that this is the limit as x approaches infinity. What is the derivative of log x? It is 1 over x. What's the derivative of 2x? It is 2. So this is the limit as x approaches infinity of 1 over 2x. And in this case, that is 0. So that is your green or t limit. And you're plugging that in here. And so the answer is 1. Okay, so that's the answer of the limit. Okay. All right, so where is it? This one is the answer that we have. Okay. Let's move on to the next one. The table below gives some values of f. It is assumed that f is defined and differentiable for all x. Okay. Which of the following claims must be true? All right. Well, let's see. So since f is defined and differentiable for all x, intermediate value theorem applies, mean value theorem applies, the derivative definition, that the definition of the derivative, that limit exists, etc., etc. Okay? So let's see. Let's take a look. The first one says there exists a point A in 1 to 4 such that f of A is 10. Well, let's take a look. You have that at 1, the value of the function is 11. At 4, the value of the function is 5. 10 is between f of 1 and f of 4. So there has to be a C between 1 and 4, or an A between 1 and 4, such that f of A is that number 10. So this is true by the intermediate value theorem. Okay? Since it's differentiable, it means that it is continuous. So the intermediate value theorem. Okay, now let's take a look. The second part says there exists a point B in 1 to 4 such that f of B equals B. Now, we want the function value to equal B. Well, what can we see? If we look at the function f of x minus x, since f is continuous and the function x is continuous, this difference is continuous. Let's call that g of x. And what does this say? We want to find a b such that f of b minus b is 0. Well, that means we need to find a b such that g of b is 0. Well, this is just about a continuous function, so we're not talking about a derivative or anything, so it's the intermediate value theorem again. Okay, well, when can we find a 0 of a function or a root of a function? If you find a point where it's positive, a point where it's negative, since 0 is between a positive and negative number, you know there has to be a point between where it's 0. Okay, well, let's look at f of b minus f of a. So you have g of 1 is 10, g of 2 is 5, g of 3 is 2, and g of 4 is 1. All of these g of x is bigger than 0 for all x that we know of. We don't know if in between for any values it went under. This is all that we know. So we cannot guarantee that there is a point x where g of x is negative. So we know g of x is positive for all the x's that we can see. And we can't guarantee that g of x is negative anywhere. So we cannot predict this. So we can't have that. And I'll just show you the graph of a function just to solidify this. Okay, so let's move it a little actually. So at 1 it is 11. At 2 it is 7. At 3 it is 5. And at 4 it is 5. Okay, so those are the function values. Okay, and we cannot tell. Now I will draw the line y equals x. That is the line y equals x. Okay? Now we can't be certain at all if this function is going to do something like this, or where it does cross at these 2 points or not. We don't know. It could just be that the function just is smooth. I mean, not smooth, it's just above that green line. Okay, so we can't tell that. Okay, so you cannot guarantee that. Graphically too, you can see. Okay. Okay, so number 2, we cannot guarantee. Okay, there exists a point such that f prime of c is 0. Well, certainly you have that g of 4 equals 5 equals g of 3. So there must be a point between 3 and 4 where g prime of that point is 0. Okay, so in fact, this could have been 3 to 4. Okay, and what is that? That is using the mean value theorem, which we can because the function is differentiable. Okay, So yes, we are guaranteed that there's a point where the derivative is 0. Okay, there exists a point where f prime of x is bigger than 0. Well, even for this, once again, you can't guarantee that. Well, you might, on one hand, feel like drawing this graph that I will draw. And you will say, well, in this part of the graph, let me use a different color, where you might say that in this part of the graph, that the function has a positive derivative. But it need not be like that. It could just be that the function smooths out before it reaches 3 and then is flat over there. So it could be that it could be something like this. And you still have that the function is differentiable, and there is no point where the derivative is positive. Okay? So we can't guarantee that as well. All right. So what did we use over here? We used the intermediate value theorem. We used the mean value theorem. And we were able to use the intermediate value theorem because a function that's differentiable is indeed continuous as well. Okay? Okay. Let's look at this next one. So we have functions f and g are differentiable, and table gives the values of f, g, f prime, g prime. Okay? And you're supposed to find h prime of 1. Okay. Well, let's take a look. We have that h is the composition of g and f over x. All right, so let's write down what's the derivative formula. H prime of x was f and g are differentiable, x is differentiable, so we do have that this composition is differentiable as long as you stay away from x equals 0. So what is h prime of x by the chain? Well, it's g prime of f of x over x times the derivative of f of x over x. Okay, so what is that? G prime at f of x over x. And what's the derivative of f of x over x? It is x times f prime x minus f of x times the derivative of x, which is 1 over x squared. All right, so that is h prime of x. So what is h prime of 1? It will be g prime at f of 1 over 1 times 1 times f prime of 1 minus f of 1 times 1, which is just that, divided by 1. Okay? So that is just g prime at f of 1 times f prime of 1 minus f of 1. Okay? So you can actually find the exact value. What is f of 1? Well, let's see. F of 1 is 5. So this is g prime at 5. What is f prime of 1? That is 8. So this is 8. We already saw f prime of 1 is 5. Okay? What is g prime of 5? For that, we need this. And that is 9. So 9 times 3, which is 27. All right? So you have that h prime of 1 is between 20 and 30. All right? Okay, so let's move on to the next problem. And let's look at this. What do you have? You're given 4 points, 1, A, 2, and B, where A is strictly between 1 and 2, and B is strictly bigger than 2. And you're given this function, f's derivative, f prime of x is x minus a over x times b minus x. Which of the following must be true? The function's decreasing on the interval, has a local minimum, has a local in the interval 1 to 2, has a local minimum on the interval 0 to a. So you look at this question and you ask yourself, what does this have to do with? And you see what this has to do with is derivatives increasing, decreasing, and critical points, local maxes and mins. Okay, so let's draw a number line like we do when we look at derivatives and increasing, decreasing. I'll put 1 over there, I'll put A over there, I'll put 2 over here, and I'll put B over there. Okay, and we will look at the sign of f prime. Okay, well, let's see, let's write down f prime of x equals, and just to make it easier, I will use this. X minus A x, and I'll use a fourth color. Whoops, let's use pink for B minus x. Okay, all right, so the question part 1 says is as if the function is decreasing over A to B. All right, well, let's take a look. If you have an x in here, what's going to happen? X minus A, the numerator will be positive, correct? X in the denominator, that is positive too, because it's bigger than A, which is bigger than 1, so it's certainly positive. How about B minus X? B minus X, that's also positive because X is smaller than B, because X is between A and B. So you have that last thing is also positive. So this whole quotient, f prime, is positive. So because this is positive, you do not have that the function's decreasing on the interval. In fact, you have that the function's increasing on the interval A to B, okay, because the derivative is positive. All right, now let's look at the second one. It says the f has a local minimum in the interval 1 to 2. Well, let's take a look at this. Okay, on the interval 1 to 2, what do you have? X minus A over x times b minus x. You know, this is all well defined. There are no zeros anywhere. B minus x is non-zero. X is non-zero, so you're not dividing by 0. Okay, so I'm going to put this on the side over there. Okay, and let's take a look at whether there's a local minimum in that interval. When will you have a local minimum? You have a local minimum if it's a critical point. When is there a critical point? Either f prime is 0 or f prime is undefined, but f is defined, okay? In this case, because the way the f prime is x times b minus x, it's only going to be undefined if x is 0, if x is b. So certainly not in the interval 1 to 2. Okay, so let's see. Does it have a local minimum in that interval? Let's look at the sign of f prime in the interval 1 to 2. Okay, if x is in 1 to 2, what's going to be x minus a? If you're in 1 to 2, well, let's see. Let's take each of these separate. So suppose you're in the interval 1 to a. Okay, x minus a will be negative. That's the numerator of f prime. Okay, and let's look at the denominator. X, that's by itself positive. I'm just using this over here. Okay, and then the pink term, b minus x, of course, that's positive. So you know that from 1 to a, you have that the derivative is negative, so the function is decreasing from 1 to a. Of course, at x equals a, you know f prime is 0. Because, you know, you'll have a minus a, that's 0, and that denominator is non-zero. Okay? So if you want to write it down over here, it's a minus a over a times b minus a, and that is just 0. Because that is not 0, and that is not 0. Okay? And then how about if x is between 2 and a? Let's look at each one of these again. Then what do you have? You have that x minus a, that will be positive. The numerator is positive. Let's look at the denominator. X is always positive. And what about b minus x? That is positive. So, just so that we have more space, let me move this. Okay, so what's going to happen when you have an x between 2 and a, you must have that the derivative is positive. So you have that. You know f prime is 0, it's decreasing to the left, it's increasing to the right. So by the first derivative test, you do have that f has a local minimum in the interval 1 to 2. Okay, and in fact that occurs at a. Okay, and you're asked, the third thing is f has a local minimum in the interval 0 to a. Well, what if you're from 0 to a? Let's put a 0 over there. What's going to happen? If you are, it doesn't matter, as long as you're in the interval 0 to a, x minus a, the numerator x minus a will be negative. X is positive because you're in the open interval 0 to a, and b minus x is positive. So in fact, over this whole interval 0 to a, you do have that the function's decreasing. So I could in fact draw this arrow like this. So that is not true. So you can only deduce that f has a local minimum in the interval 1 to 2. Okay? What did you do over here? In this problem, all you used is you looked at this derivative function and deduced what the signs of the derivatives were and used your knowledge of critical points and the first derivative test. Okay? All right. Let's move on to the next problem. In this problem, you're given values of f and f prime, and you're assuming that f and f prime are continuous. Of course, if f prime exists, it means that f is differentiable, so it is continuous anyways. And you're asked to find the linearization of this function h, which is x squared times f. Okay, what is the linearization of a function? What will that be? The linearization at some point a. What will that be? It will be h of a plus h prime of a times x minus a. That is the formula for the linearization, right? It is the equation of the tangent line to the graph of h at x equals a. Okay, so what will h of a be? It's a squared f of a. What is h prime of a? Well, let's write down what is h prime of x. It'll be 2x f of x plus x squared f prime of x. So it's just using the product rule. So that's what you will have. Times x minus a. Okay, so you want the linearization at 3. So LH of x at x equals 3 will be 3 squared times f of 3 plus 2 times 3 times f of 3 plus 3 squared times f prime of 3 times x minus 3. So you just plug in the values. What is this going to be? What is 9? What is f of 3? It is 2. 2 times 3 is 6. F of 3 is 2 plus, what is f prime of 3? F prime of 3 is negative 2, and you're multiplying that by x minus 3. Okay, sorry. Okay, well, we will look at this. So what is this going to be? That is 12 minus 18. This is minus 6. This is 18. And that's what the formula is. I mean, we can see if anything matches that. And if we take a look, we do have 18 minus 6 times x minus 3. Indeed, you do have that. B is the linearization. Okay? All right. Let's move on to the next one. You have a function that's continuous on the interval with a continuous derivative. Which of the following statements must be true? Okay. If f of x, integral from a to b of f of x is 0, then there has to be a point c in there where f of c is 0. Well, if you remember, what does the mean value theorem of integration say? It says that if you have a continuous function, then on the interval a to b, if you look at the integral of that continuous function on the interval a to b and divide that integral by b minus a, then there has to be a point c between a and b such that f of c is this interval. Okay? So what do you have? You have that if this integral in this first part, if that integral is 0, that means that this is 0, so there must be a c where f of c is 0. So that is true. Okay, this is by the MVT of integration. Okay, part 2. Is there a c where f of c equals 1 over b minus a integral a to b f of t dt? Yes, exactly same thing by the mean value theorem of integration. Okay. Now, let's take a look at the third choice we have over here. Derivative of a to x f t dt minus integral a to x f prime t dt is f of a. Is that f of a? Well, let's take a look. What is the derivative of a to x f t dt minus integral a to x f prime t dt? Well, what do you know? You know f is continuous. So here we're differentiating an integral of ftc1 comes into play. And continuous derivative. So f prime is also continuous. And ftc2 will come into play over there. So by the fundamental theorem of calculus 1, what do you have? The derivative of that will just be f of x. Okay? Now ftc2, what does that say? What will that be? It'll be f of x minus f of a. Because f prime is a derivative of little f, or little f is an antiderivative of f prime. You have that by ftc2. And if you simplify this, this is indeed f of a. So yes, that is also true. Okay? And looking at this last choice over there, what do you have? Let's use a different color so it's not too weird. What is the first derivative? By ftc1, this is f of x, which is applicable since f is continuous. And if you want, you can think of this as switch the integrals, switch the limits and make a minus, and then apply ftc. You know that in this case, it is also f of x, but with a plus of a minus. This minus because you have to switch these two. So this is indeed 0. So that is also true. Okay? All right, so we're using the fundamental theorem of calculus over the here and the mean value theorem of integration. Okay? All right, let's take a look at number 9. We have limit as x goes to 0 of f of x over x is 6, and limit as x goes to 0 of g of x over x is 2. Then which one of these limits are correct? Or is there insufficient information, or does it not exist, or is it none of these? Okay, well, let's take a look. If you take a look at this problem, all of them involve f of x over x plus g of x. Okay. So, well, let's take a look at what is f of x over x plus g of x. There's multiple ways you can do this problem. We're looking at the limit as x goes to 0. Well, first, what you can do is, one of the ways is multiply and divide by 1 over x. And what do you have? Limit as x goes to 0 of f of x over x divided by 1 plus g of x over x. Okay, limit as x goes to 0 of the numerator, we know that's 6. How about the denominator? This is 1, that stays 1. The limit of this is 2. So this limit will be 6 over 1 plus 2, which is 6 over 3, and the answer is 2. Okay, so you know that is true. Another way you could do this problem, well, you could look at 1 over the function whose limit you're asking for. So let's find limit as x goes to 0 of x plus g of x over f of x. Okay, that is limit as x goes to 0 of x over f of x plus g of x over f of x. Okay, well, what is the first one? You already know limit as x goes to 0 of f of x over x. So this one will be 1 over 6. How about this? Well, this one you can multiply and divide by x. Oops. And the answer is 1 over 6 plus 2 over 6. So that's 3 over 6. But that's 1 over the limit, right? Because that's 1 over that limit. So this one is 6 over 3, or in other words, 2. Okay? And either one you use is fine. Okay. Now let's look at the next one. Okay. We have a graph of a function. G of x is integral from 0 to x f of t dt. So it's the net area from 0 to x of this function f. So if x is here, it is minus of that area. And if x is here, then it's minus of this area plus this area, or the area above the x-axis minus the area below the x-axis, whatever you want to say. Okay? That's one way to think of g. Also, you do have that g prime of x by ftc. Since f is continuous, you can see the graph of f, it's continuous. You have that this is f of x. Okay? So g prime is given by f of x. So the question, part 1, is the function increasing on 0, 2? If the function's increasing on 0, 2, you can word this in other ways. That is g prime x positive? And g prime is f, but f is negative on 0 to 1. So the answer is no. Okay? Or you could also ask, you don't need to look at the derivative, you could also think about the area. What if you're looking from 0 to x? What happened at 0, integral 0 to 0, f of t or x dx is 0. But as you increase x, what's going to happen? This gets more and more negative as it's the net area, and that's negative. So it actually went from 0 to something negative, so it decreased. Okay? Makes sense? So in fact, g, whether you look at it this way or just looking at the net area, decreases from 0 to 1. And then at 1, it is very negative, or whatever, it's the lowest it can be. And then you're adding positive number to, increasing and increasing values to that value of g of 1. Okay? So this is wrong. It is not increasing. Okay. The function's increasing on 1 to 3. Well, let's take a look. Well, what is g of 1? G of 1 is minus of that area. And then what's going to happen? When x is there, you've added this positive number. If you increase the x, you add this bigger positive number. If you increase the x, you're adding more and more. So yes, you do have that g is increasing on 1 to 3. Or you could look at the fact that g prime is f of x, and g prime is positive between 1 and 3. So that is certainly true. Okay. Now, does g have a local maximum at x equals 2? Well, when does a function have a local maximum? A function has a local maximum when its derivative is 0, or its derivative could be undefined. Okay. But in this case, the derivative is f of x, and the only spot over here where the derivative is 0 is at 1. And that is 0, and of course at 3 also. Okay? So, and what do you have? You can also analyze it by the area. You have this negative area, and you're adding more and more area. Till 2, you've added this, and then you go further. You're adding more and more. So it's in fact increasing from 1 to 3. So of course, since it's increasing from 1 to 3, it cannot have a local maximum. Okay, so that's not true. The function g is concave up on 0 to 2. When is a function concave up? A function's concave up when the second derivative is positive. So the question is g double prime positive from 0 to 2? Okay, well, let's take a look. What do you have over here? What is this red graph? Now you will have to use FTC and realize that this is the graph of the derivative. Now you don't have a choice. Okay. What is happening to, this is the graph of g prime. What is g double prime? G double prime is the derivative of g prime. When is g double prime going to be positive? It is if g prime is increasing. You agree? And of course, this is the graph of g prime. It is increasing, so you do have that the function's concave up on 0 to 2. All right? So what we've used over here is the net change, the net area for an integral and fundamental theorem of calculus. Okay? And we've used that derivative is positive, the function's increasing, when a local min or max occurs using the derivative, or you could study it by looking at the area. Okay? All right. Okay, next question. F of x and f prime of x are differentiable. That means f is continuous. F prime, of course, f is differentiable, so f is continuous. And f prime is differentiable, so f prime is also continuous. Okay? And you're given these values of f and f prime for all these numbers. Okay. And if you look at all these questions, what they're dealing with is this integral. Integral from 1 to 2, oops. You're dealing with the integral from 1 to 2, x times f prime 1 plus x squared dx. Well, what do you see over here? You have to evaluate a definite integral, okay? But you don't have just x over there. You have 1 plus x squared. So what do? Look at this. What can you do? Well, if you stare at this, you will notice that the derivative of 1 plus x squared is 2x, and you kind of have it right there. So you should try and use a u substitution and see what happens. Okay? So let's see. Integral 1 to 2. X times f prime of 1 plus x squared dx. Okay. So let u be 1 plus x squared. Du dx is 2x. So 1/2 du is x dx. Okay, so let's do this. That part will be 1/2 du. Okay, change the limit. If x equals 1, u will be 1 plus 1 squared, it is 2. And if x equals 2, u is 1 plus 2 squared, and it is 5. So this integral becomes 2 to 5 f prime u 1/2 du. Does that make sense? Okay. Throw the 1/2 out. Okay. And what do you have? Now it's just the net change theorem. Okay, so what is f of 5? It is 32. What is f of, what is f of 2? It is 4. So it is 28 over 2, and that is 14. Okay, so you do have that D is the correct answer. All right. What did we do over here? We did a use substitution, and we used the net change theorem. Okay. All right. This is the last one we'll look at. Assume that the function f is positive and differentiable for all x. Which of the following must be true? Okay. So let's take a look. Let's look at the first one. What do you have? You see that there's arctan and there's 1 over 1 plus x squared. You know the derivative of arctan is 1 over 1 plus x squared. So let's take a look at the first one. And you have, if u is arctan x, du is 1 over 1 plus x squared, du dx. So du is 1 over 1 plus x squared dx. Okay, so the integral becomes integral f prime u du. So that is f of u plus c. Okay, so that's correct. Let's look at the this one. Okay, now this one I don't see a function and its derivative anywhere. Okay, you have an x squared and a sine x. Well, what do you have? You have the integral of this function from minus pi to pi. What's going to happen? Well, what can you do? Well, take a look. If you were not given this part, what do you have? You just have the integral of sine x from minus pi to pi of f of x squared. Correct? Okay. And you know that that has to be 0 because sine's an odd function. Okay. Well, what about f of x squared? What's that going to be? Well, that part, that will just be an even function, right? F of x squared is even function because you have that f of minus x squared is f of x squared. Okay, so let's take a look at f of minus x squared times sine of minus x. What is that going to be? It is going to be f of x squared times minus sine x, which is minus f of x squared times sine x. Okay, so what does that tell you? It tells you that this function is an odd function. All right? And when you integrate an odd function over a symmetric interval like this, what must you get? You must get 0. All right? So if you remember, we looked at things like well, this one would be the area under the semicircle. This integral will be 0, so you work this out just like that. So it's very similar to that. Okay? So this one is true as well. All right. Okay. So now let's look at this. What do you have? Once again, I see in the integral side, I see x cubed and x squared. Derivative of x cubed is x squared. So I will look at this integral. Let u equals x cubed. Du dx is 3x squared. I just have an x squared. So 1/3 du is x squared dx. And what will this integral become? This integral will become, I'm just doing the inside part first. That part is 1/3 du. And that is f of u. Okay. And When x is 1, u is 1. When x is 2, u is 8. So you have 1/3 integral 1 to 8 f of u du. That's all we get. We don't have an f prime or any such thing. And then, even if we did have an f prime, it would be f of 8 minus f of 1. But here we have an f. We don't know what the integral of f is. So what we have over here is not true. Okay? All right. Even if you did have an f prime here, then you'd have f of 8 minus f of 1. Okay? So in either case, this is not true. Okay? All right, and let's look at the fourth integral that we have here. Minimize all this. Okay, and over here too, clearly I see there's an e to the x and its derivative e to the x. So let u be e to the x. Du dx is e to the x. So du is e to the x dx. So this part will become du, and the inside part will become when x is a, u is e to the a. When x is b, u is e to the b. So it'll be e to the a to e to the b. The thing, the telephony thing will become du. This is f prime of u. So what will this be? F of e to the b minus f of e to the a. So it is not f of b minus f of a. Okay, what did we use in this problem? We used u substitution and the fundamental theorem of calculus. Net change theorem 1. Okay, I hope that made sense. Do contact me if you have any questions. Bye.